Okay, so I'm Phil White, Chief Architect at Scale, and this presentation is about Scribe, our storage layer, and some of the decisions and components that went into building that. This is sort of a list of minimum requirements. I think these sort of go without saying. I don't know that we need to really discuss them. If anyone disagrees with anyone, we can certainly talk about it. But guarantees consistency. These are block devices for virtual machines. They have to obviously be consistent. No single point of failure. Scalable in capacity and performance. As Scott mentioned, you can add nodes and remove nodes online. And as you add new nodes, you want both capacity and performance to scale along with that. Obviously, high availability. And then live migration, and then also that in concert with non-disruptive upgrades. You want to be able to allow the user to click one button on the UI and upgrade everything in the system, including host kernels and everything, with one click. And that's fully automated, including live migrating your VMs around in the background as this is happening. So that is a really sort of amazing feature, and that's considered a minimum requirement for us. We want to make these sorts of things as easy to use as possible. So getting into Scribe, into the actual storage layer, it's very modular, and these are probably 5 of the more significant modules that we're going to talk about today. First of all, QEMU libscribe. Now QEMU, if you're familiar with KVM, that's the user space process that's actually going to be running a virtual machine. So your guest VM is actually running within QEMU, and libscribe is sort of our integration point between QEMU and Scribe. It's just a component that we sort of added to QEMU so that it could natively support Scribe. The VSD Engine, and you'll hear this term a lot. VSD is just virtual Scribe device or virtual storage device, but that's basically the virtual disk image that's presented to the VM. And the RSD placement spec, a subcomponent of the VSD engine, but this is it's really an algorithm that is responsible for selecting which disk data gets placed on, and I'll go into that in more detail. And then the RSD engine, which is responsible for allocating and maintaining reference counts of blocks on real devices. And again, I'll get into this in a little bit of detail here in a minute. And then lastly, a critical piece of Scribe, the cluster map, which is really sort of a consensus module. Anytime you have a cluster of machines, there are a few critical decisions you have to make that you have to have consensus among all the nodes to make those decisions, and you need some sort of a consensus algorithm to do that. And the cluster map, which we use a piece of software called Log Cabin. I'm going to talk about in a little bit of detail on that. It's a pretty interesting component.
Before you leave that slide,
yeah.
So there's 2 things I want to say here. One, all the stuff works together, and so there's a little bit of a chicken and egg thing. We really struggle with how to explain this to people, because when you're talking about the VSD, you're referencing RSDs, and when you're talking about the RSDs, you're referencing VSDs, and you kind of need some basic stuff. So just to kind of hit it again, the VSD engine that's what manages. There's one VSD engine for every virtual device, every virtual block device in the system. And there's one RSD engine for every physical device in the system. So those are 2 key points. The other thing is, a lot of this stuff is going to sound familiar. It's going to sound like things that are in other products that sound like similar to lots of other things. But there's something a little bit unique, a little special about each one. And when you put those together in concert, it makes the whole thing really special. So if you kind of have that feeling like, oh, this is just like that, ask why it's different, because it is.
So this diagram sort of illustrates how everything fits together, and you'll notice there's no lines here for nodes. There's no. This is sort of a cluster as a whole. So you've got all of your VMs that are running on the cluster on the left, running in QEMU processes. And then on the very right, you have all of your block devices. These are the actual physical disks connected to all your nodes. So QEMU process is attached to a few VSD engines, one for each virtual disk that's connected to that VM. And then those engines use as resources really all of the RSDs as well as log cabin, which they're accessing over the network. There's also an optimization for local disks. You're not talking over the network if you're going to local disks, and there's actually a pretty cool optimization in there, which I'm going to talk about here in a moment. But
so the virtual machines read from the disks locally?
They do. Yeah, if they can read either, so they can read over the network, but the idea is that each virtual machine, each disk on a virtual machine can talk to any disk in the cluster.
Okay.
The local path is an optimization that if you're local, don't use the network, read directly from the local disk, which we actually do over shared memory, and that's.
But the VM can move from node to node in the cluster.
Absolutely.
Live.
Yep.
Right.
Live.
So I mean, you can imagine like to make high availability work, the data has to be stored in two places on the cluster. One copy might be local, one is definitely remote.
Right.
And so when you go to write, you have to write to both places. So the VSD is going to talk to both RSD engines, and send that data. One might be local, the other remote. And when that write is acknowledged by both sides, then we acknowledge it to the guest.
Okay. So what happens if the machine moves to a different node? Does any of the data move along with it to try to keep it optimized, or?
No,
it can be.
I mean, at 10 gig, the latency is so low that it really isn't much of an issue. As we move into flash, that might become more important. But with spinning disk, the overhead is very.
The algorithm says if the data is local, use that.
Right.
Correct.
It definitely, if you're doing a read and the data is local, it gets it locally.
But it doesn't make any attempt to try to keep it local.
Right.
Okay.
Right.
Right.
Because one of the things is it's kind of a core design tenet of ours is that all nodes in the cluster are equal, right? There's no master node anywhere. There are masters that get elected for specific purposes, like in the log cabin thing, you have to have a leader, but that is elected and that can move around. If that node dies, we just elect a new one. So there's no critical piece. There's no, we're not storing anything critical on one specific node in any situation.
Okay. And is there a specific type of fault tolerance on the data? Like, do you write it to
two
nodes?
So right now we write it to 2 nodes. It's single mirror or whatever, 2 copies.
Yep.
That's how we ship. One of our again with just making things easy. That's how we ship for everybody. We'll talk about it in a minute, a little more detail on the VSD engine. So
with the RSD engines, are you guys doing RAID on the drives, or is it RSD engine per
RSD
drive?
engine is we assume the RSD is totally unreliable, and it's just a single place to store data that may go away.
That way, it gives that decision to the VSD how it wants to implement reliability, if it even wants to implement reliability at all. There's a possibility where with this design, you could implement a VSD engine that was just like, okay, store the data on one RSD.
So redundancy is handled in hardware. You're not leveraging the RAID controller in the Dells or anything like that.
Right.
No,
So redundancy is handled by the VSD engine itself.
Yeah, in the software. Yeah. So let's dive in a little bit to the libscribe component here. As I mentioned before, this is the point of integration between QEMU, the VM, and libscribe. And the important thing to note here is that this doesn't require any special drivers in the guest. This integration point, this libscribe component, is actually part of the QEMU process, and it presents a virtual device using just the standard VirtIO interface. So as long as you have the VirtIO driver for the guest, these disk images will appear to the guest.
And we can emulate IDE as well. So
yes.
So you don't need a driver, but the difference in speed is so much that you would never do it without.
So one of the nice things we get from this integration as well is that because of the way we integrated it, it's essentially acting as a supported device type under QEMU. So all of the off-the-shelf sort of command line tools, converting disk images to and from, either QCOW2 or whatever, that stuff just works. And we're able to leverage that for VM import and export. It was a pretty easy feature for us to develop as a result. We can pull a VM in off of an SMB share and immediately just dump it right into Scribe using this point of integration. And then this is, I mentioned earlier, shared memory. One of the things we wanted to do was keep the latency as low as possible, especially if that copy of the data is local. And so we This is one thing that a VSA really can't do, and that is share this memory buffer all the way down the stack. So you have a guest that is doing I/O in and out of a buffer that is allocated by our libscribe component here. We're just passing essentially a pointer all the way down to the hardware. And we never copy that data. It stays in the same buffer when it gets written to local disk as well as when it gets written to the network. So we're not making copies there. So that gives us this really low latency path to getting that I/O started on the actual device. Okay, so moving on to the VSD engine. And this is, I think, where most of the technology in Scribe lies. This is really what's implementing sort of the reliability behind a virtual device. So, as we mentioned before, a single VSD engine, which there's one VSD engine for every block device, it's able to talk to all of the RSDs in the cluster. All of those real devices, all your disks, all your SSDs are available to a single VSD engine. And as well as the cluster map. And that comes into play with us. For example, we store the root metadata for a VSD in the cluster map. It doesn't get updated very often because updating those sorts of values are somewhat expensive. You have to go through the consensus protocol, and that has a little bit of a higher latency. But for the most part, you're talking just to RSDs. And the VSD engine has a few different implementations. So we wanted this to be modular. We want to be able to have different implementations of a virtual device running side by side. If you want to have a virtual disk that's doing just mirroring, running side by side with a virtual disk that's doing erasure coding, this is what this gives you, right? And they're using the exact same underlying physical hardware, so you don't have to, worry about which disks are utilized by which virtual device. So our shipping production implementation of a VSD right now is called Reliable VSD, which these sorts of things are what are implemented in the VSD engine. The immediate consistency, that's typical block device semantics. When I issue a write, when that write returns, it's guaranteed consistent. There's any failure that occurs immediately after that point, you're guaranteed that any read after that write is going to give you that same data. You have to have that for a block device. The metadata is very lightweight. We use 1 meg blocks by default, and that gives us about 8 megabytes per 1 terabyte allocated. The nice thing about that is that that's very easy to cache in RAM, and we do that when we bring a VSD online. We load all the metadata into RAM, and so that way any of your reads are not going to touch disk for metadata. Writes obviously have to touch disk. That's part of that guaranteed consistency. But the metadata very lightweight, very fast. Metadata also being stored on the RSDs right next to the data. So, by default, using 2 copies of the data and metadata.
It does support up to 16. We just haven't shipped that yet. So, and obviously 16 is insane. But.
Yeah, totally extreme. And then snapshot and cloning is implemented in the VSD engine as well. Currently, we support about almost 6,000 snapshots with a low performance penalty. Those snaps and clones are instant. Clones are instantly writable, so it makes it easy to just click and clone a VM and then immediately bring it up, from a gold master image or something like that.
For the mirroring, do you have some notion of failure domains? Like, if I want to make sure stuff is mirrored to the other rack or that kind of thing?
Right now it's basically per node. We don't. I mean, the limits on the scaling. We don't go to huge clusters yet, so it's just per node. But that failure domain is built into the software for when we get to larger clusters.
How large can your cluster be now?
It's 8 nodes is the limit, and then we're working on 16 now. That's part of. We kind of switched over to Log Cabin recently, and that was part of that process of moving to larger clusters.
Yeah.
There's a lot of negatives to big clusters too. So, you have to start going to triple mirroring and all those kinds of things. So,
is all the inter-node communication through the top of rack, or do you cable them to each other?
Top rack.
What do you do? Is there anything that's done for a like host isolation? So if one of the nodes gets isolated from the rest of the network, what happens to the machines that are running on it?
So they're force killed on that node and then brought up on the main cluster.
Okay.
So
there's essentially a disk leasing mechanism, right, where after a timeout, that isolated node will no longer be able to utilize the consensus engine to set keys. So we realize that has basically been isolated, and those leases expire, and we kill the VM. It'll essentially crash at that point. So it comes up in a crash consistent state on one of the other nodes.
Okay.
That's still accessible.
So is it using some sort of that master, some sort of election to determine if it's isolated?
That's that consensus module, that log cabin service, which we'll talk about in a moment. It's essentially, it has to have a quorum in order to be able to update root metadata, and part of that root metadata is a lease, and it expects to be able to update that lease every 2 minutes. Right now is what we set it to. So you will know in 2 minutes that if you can't get a consensus that says, hey, I still have this lease on this VM, then you know at that point that you have to crash the VM. And so our software does that at that moment. The other nodes that are sitting on the other side of that partition are required to wait until that timeout goes by, so that they know that, okay, well, at this point it's now impossible for that VM to be running on the other side of the partition. So we're able to bring it up on the side that, where we can gain consensus, right?
Where you say crash the VM, do you have some out-of-band process to shut the machine off or something like that?
Yes, it's actually part of that QEMU libscribe. So libscribe will actually essentially exit that process. Yeah, I mean, so the VM no longer exists at that point. It just.
Cool. Can I backtrack a little bit?
Sure.
We're talking about, it's less technical about this stuff. Talking about top-of-rack switches, do you guys, if I'm a customer, I'm a small school district or small business or something like that, I want to buy a 5-node cluster from you guys. Do you guys sell top-of-rack network equipment as well? Or do I? Okay.
Yeah.
So I can buy the whole package from you.
You can buy the whole package from us. I'd say we get about 30% of the time that happens.
Okay.
Yeah. Most
and
people.
You guys will help support it and stuff.
Yeah,
I don't need to find my own network engineer or something like that.
Right.
Okay.
Right. And actually, that's
Not that network engineers are bad.
But
it's just another thing that I probably didn't think of, because the network is just this invisible thing underneath it, right? And
you
guys need a reliable one, and
so networking is probably one of the least understood technologies inside our customer base. I mean, it's hard to do networking right, and usually the install process is 15 minutes of setting up our node and an hour of troubleshooting their network. So we just make sure all that happens, because we want the customers to have a good experience when they deploy. So,
what do you require from the customer environment to deploy this thing?
Just two. Well, I mean, really one switch, but 2 switches ideally. So we have LAN access as separate from what we call the backplane, which is the inter-node communication where all the data traffic goes. And so there's basically 4 network ports, 2 for LAN, 2 for backplane. And so ideally you split the switches and you do half backplane, half LAN on each, and set that all up. So it's definitely the most complex part of the deployment.
I mean, DNS, DHCP, NTP, do you require those things from the customer?
No.
So just ports?
Just network.
We utilize them if they're available, obviously, but we don't require them.
I see.
So there's a question on Twitter about what happens if there's a partition. So what if you've got, for instance,
switch crashes?
Something like that.
It's similar to what we were just talking with your question. If you have, say, you have a 5-node cluster, and then you have a 3 and a 2 node, basically. You get a partition where you have 2 nodes that can talk to each other, 3 nodes that can talk to each other. The 2 that can talk to each other are essentially, you don't have a quorum anymore in those 2. They won't be able to run virtual machines because they can't continue to update their leases. So VMs running on those nodes would crash. Now that's the 2-node, 3-node case is actually really rare, and you'd have to have some kind of a switch misconfiguration or something most likely to cause that scenario.
Well, and in general, right now with shipping with 2 copies, there's probably 2 copies of some of the data on both those nodes, and you're going to freeze I/O anyway. So in that particular situation,
in the case where you can still, like say you were running on one of the 3 that was up, you might still be able to update your lease. But if you had a block or something that was on those 2, that I/O freezes until that partition is resolved.
Okay. So you would experience an outage basically at that point.
Yeah.
Until that.
If you have 2 nodes offline,
when we ship three copies, then that's all going to work the way it should.
Yeah.
If the switch crashes and every node is isolated, presumably none establish a quorum. They all kill their VMs.
And that's why, that's why we have the redundant switches ideally. So.
But I mean, when the switch comes back, then do they all figure out what happened and turn the VMs back on? And
Yep.
Yeah, that would be one of those situations where you'd have like, oh, my alerts, everything's going wrong. The switch comes back up. They'd probably be on the phone with support, and in a matter of probably 2 or 3 minutes, it's going to be firing up all your VMs again. So.
Well, then you're going to have to recover all of them.
Yeah, that's.
Are you in that sort of case? Do you let people, because take VMware for example, you can choose how that situation is handled. You can choose whether to an isolation event. Mm-hmm. You can actually choose. You can configure in the advanced settings. You can configure how it's detected even, but you can choose to leave VMs powered on, power them off, shut them down, that sort of thing.
So what we do is no, there's no options. I mean,
it's hard off.
The default is it has to be hard off because.
Well, it doesn't have to be hard off, but
Well, I guess you could freeze I/O and hope things come back, and that's probably what's going to happen for a short period of time.
Yeah.
But you can't allow any more writes, otherwise we can't guarantee that the write's consistent, and you might lose data, or data corruption, or all kinds of bad stuff. So, but then
have eliminated the theme in the morning seems to be I like options that allow me to make really bad decisions. So, so you guys are, as with Rubrik and other companies, you guys are allowing me or disallowing bad decisions.
Correct.
On my part. Okay.
Yes. Yeah, and so the main thing is that in any sort of event, whether it's total power off or network loss or whatever, what the cluster is going to try to do is get the cluster and all the VMs back in the state that they were in before the event. And try to do that as fast as possible. Now, there's trade-offs between lease timeouts and because you don't want a network hiccup to just kill a node, right?
Yeah. Well,
so that's why we say if you lose a node, it's 5 minutes and the VMs will be back up, because we want to. Basically, what we support is a 2-minute network hiccup before we start crashing things.
Yeah, because certain network events can take a little time. You lose.
Right.
I'm thinking of like spanning tree stuff. Like where. Stuff might be messed up for a little bit, but not a long time.
So it's always about. Obviously, we could make it 10 minutes, right? You could say, "Oh, we'll hang out for 10 minutes and wait to see if there's a problem." But if that happens, that means when the node dies, we have to wait 10 minutes before we can start the VMs elsewhere. So there's
a trade-off.
Trying to find that balance has been fairly interesting.
Really? Yeah. Cool. Thanks.
Does where the data is play into where a VM's going to start?
No. It's mostly the rest of the resources, CPU and memory, those kinds of things.
Do you have some affinity or anti-affinity rules?
We don't yet. That's definitely on the roadmap, though. Anti-affinity is probably the big one that we want.
Yeah.
There's very little reason to do affinity since all the nodes are the same. But the anti-affinity thing.
Good transition.
Yeah, the anti-affinity thing is a big one that we need to get.
And what's your biggest customer right now? Like, what would be the biggest use case right now?
Yeah, I don't know. We have lots of customers running 8 nodes at the with the top end gear. So that in theory supports almost 1,000 VMs. So I don't know that we have any customers running close to 1,000, but I have seen customers with several hundred. So
well, you're not taking You're not having call home stuff with all their telemetry and all that stuff, so you can market to them and all that stuff.
No, we don't
Value
do it.
people's privacy,
Yeah.
and stuff like that.
Yeah, I've got a very long story about
Oh, I'm done with you.
That's fine.
No, you got a very long story about what?
about privacy, customer privacy.
Yeah.
So that we're very, very, very cautious there.
Cool.
Let's just say the spyware may or may not have been invented because of us, even though we didn't do that. Long ago, different company.
Fair enough.
Okay, so we have, so this year we're going to be releasing, our Flash-based product as well, and the Journal VSD is a new implementation that we're working on right now, and that's going to be fairly key with that hardware. What this does is it really implements a write-back cache, a log-based journal that can do some really cool things on SSD, as far as doing properly aligned I/O and being able to coalesce small blocks into larger blocks and things just to be friendly to SSDs. This implementation, because of the way that Scribe is modular, we're able to basically wrap other VSDs with this journal. So you can take an existing virtual disk that you've already provisioned, that's been running, and add the journal to it. You can remove the journal at some point in the future as well. And this will work with any future implementations of VSDs we do as well. So if we have an erasure coding based VSD, we can just slap a journal on there if we want to improve write performance. And again, using the exact same RSDs as our other VSD, in this case, and I'm talking about the placement spec in a moment, the journal would prefer to place its data on an SSD, obviously, or probably will require SSD for the journal. So, speaking of the placement spec, as I mentioned earlier, this is actually a sub-module of the VSD. You can think of it like an algorithm, and it's pluggable. You can configure it on the fly as the VSD is running. We've got about 4 or 5 of these at this point, and some of the examples are, okay, we want a placement spec that's going to distribute the data for a VSD based on RSD capacity, right? So you want to put more data on RSDs that are bigger. That seems obvious. We also have another placement spec that actually chooses RSDs based on the current utilization of RSDs. That's important if you're adding another node to your cluster. Now you have all these empty disks, and you want to maybe bias your placements to those empty disks, just so you can start to balance things out a little bit. And then with the journal and with our Flash-based offerings coming up, we have placement specs that are based on the relative heat of particular blocks. So what's the particular I/O history of one block? Should this block be on slow storage or fast storage? That decision is being made by the placement spec. As far as when that decision is made, a few different times. Obviously, new allocations. If the first time you're writing to a particular offset on a VSD, we need to allocate some space for it. We consult the placement spec. Migration, if we're doing a rebalance as part of a node add or something like that, we ask the placement spec to sort of take a look at all the data as part of a VSD and decide where should that data be. And then lastly, recovery. You have a write error or a drive fails, we go to the placement spec to say, okay, where should we put this data? This is where those failure domains come into play. The placement spec is what is aware of the failure domain, or the failure ID as we call it, for each RSD ID. Other things that it can look at, the used space on an RSD, the capacity of the RSD, and locality is one thing that's available to it as well. So that's available for a future implementation if we choose to do, write data locally to this VM. All those sorts of parameters are available to the placement spec. And block heat is what comes into play with the with tiering. So the placement spec will be aware of how frequently a particular block is being accessed, and it can use that data to make a decision where to place it.
So are those the only time that runs is during a node add or a new VM? Like, does it run?
It runs on one particular. I'm sorry.
Does it work in a kind of a way like DRS to balance clusters out without any interaction?
Yeah, so when you do a node add, as of right now, it's a manual process to trigger a rebalance to say, okay, we want to redistribute the data to take advantage of all the spindles we have now. When you trigger that, it's going to go to the placement spec to ask it. And then additionally, on new allocations, on failures, those sorts of events, that's when it's going to the placement spec. So getting to the right side of the diagram
Before
here.
we jump to that, I wanted to say something. We'll back up 1 second. So one of the things I wanted to show here is you can see like these different colors. One of the things that's really cool about the modularity of the system is that you can kind of pick and choose your VSD engine and your placement spec together to give you a particular set of features for a single virtual disk inside a VM. So you can say, in this example, maybe we've got one VM that's just standard mirroring, one that's got mirroring and like hot block placement and the journal, and then this one might be erasure coding with a journal and hot block placement. So you can kind of mix and match for the right needs for that particular virtual disk inside the system. It really gives us a lot of flexibility.
Cool. Okay. So the RSD engine. As we mentioned earlier, there's one of these for every single block device in the cluster, every hard drive, every SSD. Similar concepts just to explain this. You can think of it like an iSCSI target or a network block device. We've done some unique things though that make this a little bit interesting. So RSDs, first of all, have a very simple API. We wanted that because we're going to be, as a developer in Scribe, I want the most easy to consume API I can think of, and so we were able to do that, and sort of eliminate a lot of the complexity of things like iSCSI when you're talking to a block device, as well as making it more powerful. So internally, the RSD engine is managing the allocations on that one particular device. All of the reference counting is handled by the RSD, and we actually implemented and integrated reference counting in the protocol that we use to talk to the RSD, which is pretty interesting. It makes it's what gives us this ability to do instant cloning and these sorts of things. One of the nice things about it is it eliminates a round trip in case of copy on write. So what I can do is actually, I can tell an RSD I want to write some data. Since the RSD is aware of the reference count of that data, it can internally do an allocate on write immediately, and then on the return trip, it's like, oh, I've written your data, by the way, here's the new address. Like, I know you weren't expecting this, but that eliminates that round trip. I don't have to renegotiate where we're going to write the data. So it's pretty interesting, and
it also puts that that allocate on write, that stuff as close to the RSD as possible. It's sitting right next to it in the physical hardware, right? So that really minimizes the overhead of snapshots and clones and those kinds of things.
And lastly, log cabin. And this is the consensus module we've talked about. Prior to log cabin, we actually had our own homegrown implementation of the Paxos algorithm, which is a consensus algorithm that's been around for a while. It's very complex though, and I think there's very few people that fully understand Paxos. And it was one of those things like you can read everything about it, and you understand it maybe for about 3 or 4 days, and then that's it, it's just gone, right? So Raft is a new protocol though. It was invented by a guy, Diego Ungaro, who's actually contracting with us now as well. Log cabin is his reference implementation of Raft. That's what we've chosen to use. So he's working with us to really make log cabin, it is production ready at this point. We've been working together now for 6 months or so to make that happen. And so Raft is a much simpler consensus protocol. It gives you some really good guarantees as far as quorum and making sure that things like disk leases are implemented correctly.
And when you guys switch to that or other things in the Linux space, that's still transparent. Like what you do.
So
absolutely.
Yeah.
We implemented a rolling upgrade for that, to go from Paxos straight to Raft.
So you guys can effectively switch from one Linux package to another as it
Absolutely.
evolves, and you're good to go.
Right. That was reasonably complex to build that, but
I
you
would
know,
imagine.
it's important that our customers don't have downtime, right? So
Yeah. And are also unaware that that's
that's even happening. Yeah.
Well, they are now.
Okay, so at this point, I mean, those are the main components of Scribe. I guess we can just open up the questions if anyone has any, anyone wants to go into excruciating detail about anything, we can do that. Or did I miss anything? Or
No.
I think we're.
No. I mean, yeah. So I mean, I think summary is this is how we create virtual block devices to present to the VMs, and all the storage underneath is very optimized and clustered and mirrored and all that kind of stuff, and the customers don't have to worry about anything, right?
So without the RAID controller involved, when a drive fails, the Linux kernel picks it up, hot add's cool with it, and rebuilds an RSD, and you're good to go.
So one of the things is, as soon as the RSD or as soon as the drive fails, we actually re-mirror the data based on using the free space that's available on the cluster.
Sure.
So there's no like hair on fire moment of, I got to get the disk replaced, and we don't have to have a hot spare or anything like that. So it's running, it's there all the time. We just use the free space essentially as a hot spare. So when you have a drive failure, it takes over, and usually we recognize the drive is going to fail before it's totally gone, and so we're able to read data if we need to off that particular drive. But the data is mirrored elsewhere on the cluster. And the nice thing is it's mirrored on all the drives on the cluster, and we're writing to the free space on all the drives on the cluster, so the rebuild's really, really fast.
And that rebuild process is kicked off by the VSD for each of the affected.
Exactly.
Yeah.
Yep.
Is there some sort of an allocation made to allow for a certain amount of failures of disks? If all the clusters are filling up on disk space and you lose a drive, does that mean that you're just like,
You get some pretty stern warnings before that happens.
When you start to approach maximum capacity on the cluster,
Okay.
we start telling you like you need to add capacity or delete something or whatever.
Yeah.
So,
okay, how about nodes? So are you able to say, if I lost a node, I'm still able to run the machines that you've got on it?
yeah.
You've got on the cluster?
Yes.
So one of the things that happens is to do a rolling upgrade, we have to be able to take a node down to upgrade the kernel or whatever. So as soon as you reach a capacity where like if a node went down, we wouldn't be able to restart all your VMs, you get a notice. And we won't start a rolling upgrade in that situation either. So, you guys work in this industry, right? So, it's often that people are pushing their systems further than they should. And you can't just say, no, you can't, right? Maybe it's temporary, maybe there's good reason to do it. So we allow them to do that, but they're aware. There's conditions set, they get an email. Like if you lose a node, we can't bring everything back up.
Do you want to show heat map?
Yeah, we're gonna do that next.
What about, and maybe you mentioned this, and I've just been looking at Twitter or something like that, but replication. Do you guys do any sort of remote replication?
Yeah, so we do asynchronous remote replication.
I did not demo that.
Yeah.
It's my fault.
It's okay.
So the replication is very cool. We basically, with our snapshots, which are very lightweight, we just send snapshot diffs across the wire, replay them on the other side.
Is it a one-to-one, or can if I'm like a managed service provider or something like that, reselling or working with customers that have bought your stuff, could I buy a scale implementation and have basically a multi-tenant?
Yeah. So right now, right now we support many 2-1, so you can have multiple clusters. You can't go from one cluster to multiple places.
Okay.
It's in the design, but it's really complex. It's hard to test.
Given the cost of DR and all that sort of stuff, having a many to one sort of relationship.
And so we actually have
more of a common.
Yeah, I mean, we're rolling out something with a service provider in Indianapolis that was going to allow our customers to kind of sign up for that
cool.
and send data back to them.
Yeah. Replicate to the cloud, if you will.
Yeah.
Scale cloud.
Mm-hmm. Yeah. So and the replication is super cool because you on the other side, it's basically a locked VM, and when you want to restore it, you just clone it, which is instantaneous, and fire it up. and the replication that was happening just keeps going.
Oh, okay.
So you can test your DR, make sure everything works, shut that VM down, delete it, and nothing has been interrupted. It's really, really slick.
Cool.
Now, what about traditional backup? Do you have like a VM level backup that utilizes your snapshot technology, or is it more traditional in-guest agent? How do you guys do that?
I mean, for the full feature set, it's in-guest agent, right? We have some people that buy storage-only clusters and are essentially using our replication as a backup to just a local backup cluster.
Okay.
And that's on the roadmap of things we want to do, is make that whole system.
And we do have exportable.
You can export VMs too. So if you want to export them to like an NFS share or a Samba share, well, actually we only support Samba for that, but a Samba share and then back that up, and normally that all works.
Question. You're targeting, it's a simple solution, that was your primary idea, and it's targeted SMBs. If you want to provide this as a part or a component of a turnkey solution, do you have some automation on that level, Chef integration or something like that?
We don't have Chef. We do have so the UI, the backend command line interface, and our test system and everything all use the same API. So we have an API that can be used in those situations.
Yeah, we use Thrift.
It's a very simple Thrift API, so.
Which is basically Facebook's the primary.
But we don't.
Thrift.
It's not a common.
That's my next question. Do you have any use cases already where it's used as a turnkey?
Yeah, I mean, I think there are a couple. There are like 2 or 3 customers doing it, and it's just not very common.
Does anyone use that API to do that export utility for backup?
Yes. Yeah. That's actually very common. That's the most common use cases.
Like that and UPS integration and all kinds of other just random stuff.
So I have to get water. I'm going to start a coughing fit here.
But as far as automation, you're talking about Chef and Puppet and stuff like that. What Jason demoed was a fresh install. I'm assuming that you guys we can do
you can
templates and stuff like that.
Yeah, those
you could rig a
kinds of
template
stuff.
to just join a Puppet.
No, but what I mean is the web interface or even the phone interface is interesting, but a turnkey solution, that means I create automatically X numbers of VMs with the correct applications.
Typically, I SSH in and I basically clone 50 VMs off of a template. Right?
Their skill set might be unique among their customer base.
No, it's a value. It's a VAR that would do that for you.
We have VARs that have their own VM gold images, and they just import them and start cloning and that kind of stuff. So it
is a simple solution, so it would be easy to build on top of that.
Yeah.
Those sorts of things are very easy with an API that we've done. I mean, we essentially are doing that in-house for automated testing.
Right.